workshop. I'd like to thank the organizers for inviting me, even though I told them I wasn't going to talk about free energy methods, kinetics, or Markov state models. So if you're deeply offended that I'm not going to have FEP or even any simulation in my talk, you know who to blame. What I am going to talk about is applying machine learning, specifically deep learning, to structure-based drug design. Now, of course, with structure-based drug design, the idea is you have the structure of the receptor, and you want to predict how compounds will bind, what their structure is, and rank those compounds, ideally to the level of actually predicting their affinity, so you can do virtual screening, lead optimization, guide medicinal chemistry. And as we've seen in some talks already, there's this funnel, right, where you start from the vastness of chemical space, the millions of purchasable molecules, the huge number of synthesizable molecules, and then you want to get down to some number of hits. And so the first level of that funnel might be a really fast matching approach, like you can do pharmacophore shape-based matching. Just out of curiosity, who here actually does virtual screens, like occasionally? Great. So you all know what a pharmacophore is? Right? Yeah, okay. And that's useful for screening. And so we developed these sublinear time algorithms for searching for pharmacophores and also doing shape matching. And they're implemented in this website, Pharmit. So I really encourage you to go check this out. You can screen millions of molecules in seconds, and we're not cutting any corners. It's just the power of algorithms and computing. But once you get those hits, you'll have thousands of hits, tens of thousands of hits. You need to somehow rank them. And that's where scoring comes in. And so at its simplest, the protein ligand scoring is just give me a snapshot of the protein and the ligand and give me some score, and then I can use that to say if it's a good pose or what the affinity is, right? And that's a subroutine for docking and energy minimization and virtual screening and all this stuff. And the most common approach is to use pairwise potentials, and what I'm showing here is the AutoDoc-Vena scoring function, which is an empirical scoring function, and it works fairly well. I actually think it's one of the better free versions, and the free is an important modifier there. And it's what we're going to be comparing to, right? And after this, the funnel, what I have learned at this workshop is all of this is a pre-filter for FEP. That's the point. However, in actuality, I'm not going to talk about dynamics at all. We usually just stop right here because this is what we're interested in, is the scoring and evaluating the scoring. So we don't do a post-filter of FEP. And the question is, with the scoring, can we do better? And like across the board, predicting poses and virtual screening and affinity prediction. And the key thing here is we don't want to sacrifice performance. We're in the domain of high throughput screening. Right, so we're not looking at simulation-based methods. We want to be able to evaluate thousands or even millions of poses a second. And the key idea is to leverage the power of buzzwords. So when we started, big data was the big buzzword, and I've transitioned into deep learning very successfully. But there is a lot of data. And you look at PubChem, hundreds of millions of bioactivities. Now, most of those are inactivities, but that's still data. Over 100,000 structures in PDB. You take the intersection, you still have more than 10,000 annotated structures. And that's a very rich data set to apply machine learning. So if you don't know what machine learning is, this is all you need to know in one slide. You take your input and put it into a bunch of features in X, and it's a capital X, and you put it through a black box model, and out comes a Y, it's a lowercase y, and that's your prediction, right? So it might be affinity prediction, might be whether it's a good pose or not. And the particular black box model we're going to use is neural networks. And this is a model where you take your input, those X features, right, which are numerical, and each neuron computes a nonlinear function of all its inputs, and you connect them all up to send to more neurons, and you get some output, and that's your prediction. And it turns out this is a really expressive model. You can prove that they're capable of approximating any continuous function over a bounded domain. Of course, this theorem doesn't tell you how to find the network that does that. It just says it exists somewhere. And more recently, deep learning has been all the rage. There's nothing mystic or profound about deep learning. All deep learning is there's multiple layers here. There's multiple levels of representation. There's not just one layer in your neural network. That's really all it is. And what this allows you to do is recognize higher order features. And the way these are trained is you just initialize the weights randomly, you push an example through, you get some answer, and during training you know what the right answer is so you can compute a loss, and then you apply this back propagation algorithm, which is just calculus, to update the weights of the network appropriately. So this algorithm is telling you how to correctly assign blame for that loss to the different components of the network and to fix them. And we'll come back to this later. And this approach has been outrageously successful. So I think if you went 15 years ago and got the top computer scientists in the world together and asked them, are computers going to be able to beat humans at Go, like good humans at Go? They would have all said no, and not in their lifetime. And yet Google, with AlphaGo, using deep learning, has beaten the world champion at Go quite conclusively. So that's maybe the most impressive algorithmically, though maybe a little boring. This one's cute. This was at an NVIDIA conference. They had a little deep learning thing running. Oh, you can't see it, right. Where they take your picture and looks at it, identifies your face, and it figures out what your emoji status is, right? So I was frowning, so it's sad. And of course, you know, you have Amazon and Google listening to you in your homes now, and they're using deep learning to figure out what to send to the NSA. This is a picture in Pittsburgh. This is an Uber self-driving car. Maybe you can see there's sensors up here. This is BSD3. This is where I work. Fortunately, we have a BSL level 3 laboratory in there, so we have all these concrete barriers, so we're safe. But this is what's driving, pun intended, the self-driving car resolution is this deep learning technology. And one really key area where it's been super successful is image recognition. So that when you upload your images to Facebook, you know, it identifies who's in it and all that. The image recognition problem, we've had this challenge ongoing for many years. Can computers identify what this is a picture of? And back in 2012, there was this big improvement when they started using this convolutional neural net approach. And all the winning solutions since then have used that approach to the point where you can at least claim that the computer's as good as humans on this benchmark. So what is this convolutional neural network? Well, it's a neural network with a convolutional filter. And so the difference with the convolution versus a fully connected is you're only looking at a fraction of the input. So this guy is only looking at 3 nodes, and this guy's only looking at 3 nodes, but they're applying the same set of weights. Right? So you're taking this convolutional filter and you're putting it over the image, and you're calculating the same function at each location, and then you just move it and calculate the same function. And so this is learning low-level features. The first layer is learning low-level features of the image. And this is, as you can see, a dog. Just to instantiate this a bit more, you know, these are hand-constructed filters. This is identifying horizontal lines, vertical lines, any edge. Right? This is an edge filter if you've ever done find edges in Photoshop. Right? And you can see that in the picture. Right? So you create these feature maps to identify where there's a horizontal or vertical line, and then the next layer can learn a higher order feature like, oh, there's a corner here, or there's a circle, or something like that. Right? So how do we apply this to protein ligand scoring? Right? So we're going to push our structure in. And the way we do that, well, instead of an image recognition where you have a 2D grid of pixels with a red and a green and a blue value, we're going to have a 3D grid of voxels where each grid point says what atoms are there: carbon, nitrogen, oxygen. So we have atom types, some notion of there's an atom here on the ligand or the receptor. And that's it, right? There's no explicit featurization. We're basically just giving a discretized picture of the structure. So you pick a grid resolution and atom density and atom types, and you're good, right? And then we're going to train neural networks to learn properties of these structures. For what I'm showing here, all the training data is the PDB bind, the refined sets, about 4,000 complexes. One key point I just want to make here is these are all actually on docked poses. Right? So we dock them with FINA, and then we just use the crystal poses to label them, whether they're low RMSD or high RMSD. And the reason we do this is if you're trained on crystal poses and dock poses, you would very quickly train a neural network to distinguish between crystal poses and dock poses. And that's not what we're interested in. We actually want to identify low RMSD dock poses. And we can use this to classify these poses as low or high RMSD, or to actually predict the affinity as a regression problem. An important factor that we have to consider is data augmentation. Right? So here, the augmentation is expanding our training set because we only had 4,000 complexes. So every time the network sees the same complex again, it's randomly rotated and translated, right? So it looks a little bit different. If we don't do that, we get the green line. We perfectly fit the data because it's only 4,000 points. You can basically memorize that. There's a calcium in this XYZ position. I know what the answer is, that sort of thing. But the generalization error is really lousy, as you expect. But if we augment it, the test performance improves and we're overfitting less, right? And this was really key, and we do this on the GPU, so it's fast. But it raises this question, if you're paying attention, and I know you were, is why grids? Because they are coordinate frame dependent. If you rotate the molecule, the network sees it as a different picture, as a different input. And we know physically it's not actually different. This is a serious limitation and problem with the approach. And you could also argue the fact that it isn't explicitly extracting pairwise interactions is a problem. So there better be some good pros, and I think there are. The grid really makes clear the spatial relationship. So the analogy I think of here is with a grid, it's basically like getting an X-ray crystal from electron density data, where the density data is labeled with the atom types. Like, that's pretty darn easy to do, right? You can extract the structure from that information. Whereas with many of the coordinate frame independent methods, which have to deal with distances, that's more like NMR structure determination, where you don't, in some cases, even have labels, right? Which is really hard to do. So I think it should be easier for the network to learn higher order relationships. It's also stupidly simple, which means it's amazingly parallel. We just blast this onto all the CUDA cores, and generating these grids is super fast. And since we're maintaining XYZ coordinates in relationship to space, this opens avenues for interpretation because we can put things back into 3D space and to explain what the network's doing. Right. So here's the model I'm going to be showing results from. It's fairly straightforward as deep learning models go. There's three layers. And at the end here, we split out. So all of these are the same layers. And at the end, we split out between the affinity predictor regression and the pose scoring. So this is just one fully connected layer here, while all the other weights are shared, with the idea being that there should be, the things that matter in the structure for affinity prediction should also matter whether it's a good score, pose or not. And if we look at the results, compared to Vina, we're doing great. There's just some improvements, RMSDs, correlations. This is the pose classification, so you see. But there is a serious issue here, which if you're a reviewer, you should and would raise, which is, and I know this because they did, this is trained on the PDB and tested on CSAR side, which is two benchmarks. And there's actually an overlap here. I think about 60% of CSAR is in PDB refined. So going back, if you're here Monday night, there's a question about interpolation versus extrapolation in these models. This is clearly showing sort of the interpolative space. If you want to have a better measure of generality, what if I'm doing an entirely new target? You need to do a more rigorous validation. And so this is a clustered cross-validation where the test set has targets that are distinct, more than less than 50% sequence identical than the training set. And of course, all these metrics go down, it's still better than Vina. Okay. So that works fairly well. One of the questions I get in showing this is, what about water? Because we all know water is important, and they didn't say there was any water in the model. And they're right. The way the water is in the model is by not being here. That's the idea of an implicit solvent, right? But actually, we can see that the network is using the empty space, the places where there's no atom density, is part of its decision, right? And so this is using something called layer-wise relevance propagation, where we can visualize where the output of the model is coming from across the different grids. And this is just showing in the empty space region, there's areas, red, where the model does not like that there's empty space there, or implicit solvent, if you will. And so maybe one interpretation of this might be that it wants the ligand to extend, or it wants the protein to more fully cover that cavity, and it thinks that would be a better pose, better binding affinity. And then there's areas way on the solvent where it's like, yeah, I'm happy there's solvent there. But this is still a very simple model. So one of the things we're just getting started with, and I don't really have any results right now, is working with GIST, where you run a molecular dynamic simulation of the, oh, I lied, there is a simulation, so I am going to talk about simulation. This is the slide. Of a receptor with the water, and then you can compute thermodynamic properties of the water and put it onto a grid, and guess what? We use grids as input. It's a perfect match. And so now we can actually have a water model, and it's a very rich water model because you actually have like entropy and enthalpy at a given grid point. And so we're going to see what we can do with this. This is working with Tom Kurtzman. Eric is going to come to Pittsburgh for the summer, so that's exciting, and hopefully we'll get a lot done with that. And so putting all this together, it looks like we can score, right? But we want to go beyond scoring, and this is where the backpropagation comes in again. All right, so with backpropagation, like I told you, you have your model, it makes some prediction, you compare it to the label, and you compute the loss, and then you update the weights, right, of the network. So you're improving the network. Well, what if you like the network? You've trained the network, it's a good network, it's working well. Let's just leave it alone and just keep going and update the input, right? So we're not updating the weights of the network, we're changing our input to make it look more like what the network would like to be a good binder or something. Right, so if you do this to images, you get something like this. This is one of the first examples back in 2015, which is about 30 years ago in deep learning research, where they trained a network to recognize a certain object. Anyone guess what object? Banana. Banana, yes, thank you. Everyone's always not willing to say that, but it's elongated, yellow, fruity thing, right? And so they maximize this to generate things in the network looks like banana, and you get this. And most of you can see banana-ishness here, right? But I think all of us recognize this is not a picture of a banana, right? And that's the issue. When we do this for our domain, we get stuff like this, which kind of makes sense. There's more oxygen here, salt bridge, great, that's good, right? And less oxygen here, and if you look very carefully, you can see a lot of it, oxygen acceptors on the receptor, and it makes sense, except the ligand doesn't actually have any oxygen there. You can't have less. It's not very useful, right? This is not a way to make a realistic ligand. And so we just keep backpropagating from the grid onto the XYZ coordinates. So we don't let ourselves change oxygens to nitrogens or remove an atom, but we can move the atom. So we don't remove atoms or add atoms, we just can move it. So put it more into this density, right? So we actually have vectors on these atoms, which means we can use it for the equivalent of energy minimization. And so this is one of the very first examples I did, and it works, all right, meaning that the score gets better. But what happens, so watch, it's going to be a movie. What happens is it moves in and it starts clashing with the protein, and I'm coloring this with our visualization technique, so you can even see things are turning red, which means the network knows this is bad where it's clashing, but that is counteracted by something it thinks is even better, and what it thinks is even better are these electrostatic interactions. It sees those, it just wants them to go closer, right? And the issue here is in our initial training set, it was all Dach poses. They're all physically reasonable. It never saw examples with severe steric clashes, so it never had the opportunity to learn from the data how to properly balance a steric clash with favorable electrostatic interaction. And so when we take this first model and try to minimize low RMSD poses, which if you minimize into the crystal structure, you get this distribution, they almost all get worse. Right? That's bad, by the way. But these are the most informative poses, because these are cases where the model is confidently wrong. You optimize it, it's like, this is a great pose, and you're like, no, it's not. So you just put that back into the training set, and you can shift this distribution by iterative chaining, and you end up with something that is not going to drive molecules into the protein. And so we can integrate this into a full docking workflow, which it's Nina, which is a fork of Smina, which is a fork of Vina. Okay. And so if you're not familiar with this, it's just sort of a bunch of Monte Carlo chains, and you're doing sampling, and then you're scoring with these scoring functions. And in here, you can either refine the pose, local refinement, this minimization, either with Vina or CNN, and then if you want, you can rescore it. And so we applied different workflows through that diagram in D3R Grand Challenge 3. I don't expect you to actually read this. The key thing is you want to be on the left, and the green dots are us. So these down here, we have examples that are almost all the way to the left, but never exactly all the way to the left, but within the error bars. And there's a couple examples where you don't do well. And so if I zoom in on this, I just want to point out that this was affinity prediction. The models that were scored for affinity prediction, these two weren't, these were posed, are the ones that do the best. All right, so with machine learning, you get what you train for. And we're training for affinity prediction. We did pretty well. It's better than VINA, and it's also better than most of the submissions to D3R, and not statistically significantly worse than the best submission for these guys. These two are cases where we just were bad across the board, and it's a little mysterious still to me because I know other groups used VINA and did much better. So there's something wrong with our post generation here. And so we're at a point where I think we can show that this works for scoring. It can be used for minimization docking. There's still a lot of work to do. I have a whiteboard full of ideas of how to improve this, and hopefully significantly so. I'm not going to talk to you about those. I'm going to talk to you about something even crazier, because many of those are crazy ideas. And so this is something completely different. Everything we've been talking about up to now fall into the class of what are called discriminative models, where you give it your example, your X, your big X, and have it predict your Y. Right? This is inactive. This is inactive. Well, you can go the other way. You can have a generative model, where the output is your big X. It's actually your protein ligand. And I should say, these are just our grids shown as isosurfaces. Right? And so with a generic generator, you might take some noise sample and just generate something. So this is basically translating between distributions, a Gaussian distribution to the distribution of all protein ligand complexes. A little bit more interesting is this idea of using context encoding. Instead of providing a noise vector as your input, provide the receptor, which you know, and generate a ligand that goes in that receptor. Right, so the analogy with images is where you take your photo and then you black out your least favorite relative, and then you have it fill it in with the background. Right? I think some of us have done this, right? In Photoshop, they actually have a tool for it. So this is context encoding. And so we're going to do this, and this part is sort of the architecture I showed you already. You bring everything down to a single what's called a latent vector, one-dimensional vector, and then this deconvolutes it back up into a grid again. Right? And so here's, this is all really early work. Here's an example of context encoding with molecules. Right? So this is the ligand that belongs to the receptor. The network doesn't see this. I'm just showing you what like a good answer would be. This is what this ligand looks like when we draw it with our isosurfaces. And the context encoding, just two different networks here. They really like to just fill the binding site with carbon. They're good at recognizing where the binding site is. They don't overlap the receptor. But it really likes to fill it with carbon. The other atom types are there, but at much lower densities. And so I was talking about this with Matt, who's the guy working on this. And we're trying to come up with different crazy loss functions to sort of correct the network. And he pointed out that the people in the deep learning community have already gone down this rabbit hole and decided that was a bad idea and left. And where they went was generative adversarial networks, right? So they basically, the secret to machine learning these days is when you encounter a hard problem, throw a neural network at it, right? So our hard problem was, well, what's the right loss function? Well, throw a neural network at it. So here is our generative network. So this is context encoding. You give it the receptor. It's supposed to produce a reasonable ligand to that receptor. But how do I know if it's a reasonable ligand? How do I tell the network whether it did a good job or not? Well, you have another neural network, a discriminator here, that takes a true example, a good ligand, and your generated one, and it says, is it real or fake, right? And then the loss for this is this whole thing, right? This guy is trying to fool this guy, and this guy is trying not to be fooled by these, and you train them iteratively together. So as one improves, you then improve the other, right? And back and forth, right? And I don't know how many people have seen this, but this is really cool. So this is this is only 10 years ago in deep learning research time because it's like 6 months. This is NVIDIA generating faces. They trained on pictures of celebrities, which is a nice way of saying attractive people. And all of these are fake images. None of these people exist in real life. All right? There's no artists painting these. These are all computer generated by this GAN approach. Right? And you can go watch the full 5-minute video here. In fact, they have a whole hour video on YouTube just showing you all of these pictures. Right? So where are we? What is the state of the art with GANs as applied to molecules? So here we are again. Again, we're not, you don't ever see the ligand. I'm just showing you what was in that receptor. So this would be it just memorizing what's in the receptor. And now this is what the GAN is generating. Now you see the other atom types. Right? This is still not physical. If we fit atoms to this, you sort of have a point cloud of carbon here. This one's actually not so bad. You almost have a ring here. So we still need to figure out the best way to turn this into actually a physically realistic molecule. And I'll just preempt right now, don't ask me about synthetic accessibility. Just don't. But I'm not at all worried about the less than perfection here, because if you go back, again, 30 years in deep learning research time to 2015, this was the state of the art of face generation, which, some of these are almost as unattractive as our president. So this was, Matt actually started on the whole CNN project as an undergrad, as a computational neuroscience major. If you're wondering if you think this was a brilliant idea and wonder how I got it, it was, oh, you're a computational neuroscience major, let's do something with neural nets. That's where it came from. Josh did the visualization work. Jocelyn did a lot of the work with the docking and the GPU. And of course, I would not be here without funding. And I'm very grateful to be here because of the invitation, and be happy to take any questions. So it's very simple. It's just if you have an atom, actually you have a 3D Gaussian around the center. That's it.
Just for the ligand or including?
For both of them, the receptor and the ligand. But the receptor atom types are separate than ligand atom types. You can do a hard shell Boolean, but there's issues with that. It's not as continuous.
So I think people like Brian Prescott Adams have tried a way of taking like smile strings or representations of molecules into a continuous space, where you could then hunt around and there's a reversible way to generate smile strings from them. Have you tried to link this up to your GAN approach so you can search in a...
well, people done GANs with smile strings already. Alexander Izyov, probably some other people whose names I've forgotten, and David Dovina.
But then you could search this space.
Yeah, they did exactly that. You have your sort of, actually an autoencoder with your latent space here, and then you have another, because you just throw a neural network at the problem. You have a neural network that takes the latent space and predicts your property, and then you search the latent space for it to maximize the property, and then once you find the place in the latent space, you generate the smile string.
So
it works.
Could you get molecules this way?
Yeah, you could do it 3D with this too, but we don't have physically realistic molecules at what you might like. The smiles people also don't get syntactically correct smile strings, but they can just identify those easily and throw them out.
So why can't you do the same thing?
We're working on it. It is so preliminary. This is really. This is if you're at ACS in Boston in the fall, I'll maybe have 3 more slides.
It's like 10 years.
Yeah.
Jacob.
By atom types, do you mean just elements, or do you include some degree of chemical information? Like an sp2 carbon might be noticeably different from an sp3, and an alcoholic oxygen is going to be noticeably different from a carbonyl oxygen.
Yeah, that's a good question. So we're actually using the Smina atom types. So it's heavy atom only, and we get the hydrogens by having donor acceptor atom types, and we have aromatic versus aliphatic. We have 4 types for carbon. But it turns out if you just went to elemental atom types, you only get a small decrease in performance. And we can actually show that the network is sort of figuring some of this information out on its own. I can get some more detail on why I believe that, but because it has the whole chemical environment.
Time for one more question, Justin.
So, what level of resolution do you need on the grids? And does your grid include the whole protein or just a region around the binding site? Like, how do you deal with the fact that different proteins are different sizes?
Yeah, we don't have size extensivity. We have a fixed 24 angstrom grid at a 0.5 angstrom resolution. The smaller the resolution, the higher resolution, again, you'll see an improvement of performance, of accuracy, but you scale with the cube for time. So 0.5 is kind of the sweet spot.
All right, let's thank David again.